Can you guys hear me now?
We got you now. Yeah, sorry. I think we bumped you a couple times, but we can hear you loud and clear.
Okay, I'm not going to press any buttons. So one more time. Yeah, this is not strictly a ham radio talk, but if you're the sort of person that is interested in ham radio, you may be the sort of person that is interested in amateur radio astronomy. So, this is, it's an intro slide, but I think there's some interesting stuff here. So first of all, happy World Amateur Radio Day. That's today. And there's a hashtag there. It's all over Twitter. There's some pretty interesting stuff going on if you chase that down. But I thought this graphic was funny, so I thought I would share it. If you have sat through ham exams, you may recall that when you go for your technician class, you get licensed to use the 2-meter band, right? I mean, you get, technician is, I think, the first one where you can actually transmit. So yeah, social distancing joke there. So what else can I say? This is the talk about amateur radio astronomy, but I want to make the point that amateur just means unpaid. It doesn't mean unskilled. It doesn't mean like you hear people use the phrase amateur night. This isn't that. Like, radio astronomy can be pretty challenging from a mental, academic perspective. So let's see if I can figure this out. I did it. Okay, so real quick, a little bit about me and my background. I'm currently, I work in security. I currently work at Palo Alto Networks, and I'm a consulting engineer. And what I do is, we're sort of an expert in an area. So mine is like automation and CI/CD pipelines and stuff like that. In the past, I've worked at Motorola. We did cellular base station products. So features for those, I was like the tech lead for those kind of features. I worked at Nokia Siemens as an R&D engineer, and then I also worked, my last job was at Salesforce. So I got to do log aggregation for big amounts of security logs. And down at the bottom, yeah, I went to college. All right. So I said all that to get to this point. So I
think we might have just lost audio. Let's go ahead and see. Make sure you didn't bump that mute button.
You guys hear me okay now?
Yep, we're back.
Okay. All better. I'm not a cosmologist. I kind of wish I was sometimes. Like, radio astronomy is fun, I think. But my background is all computers, networks, security, probably like a lot of you folks. Yeah, just that. So normally, I would present this in Git pitch. I like the clickable format. If you go to GitHub, so it's github.com/hotpeppersec, you'll see the Hack the Universe slides. So you can see like the speaker notes, the links for everything I'm going to talk about. You can put in issues there. Normally I like to say, hey, it's okay to interrupt me with a question anytime. I guess in this format, maybe send me a tweet. I almost would say just unmute the audio.
Yeah, we can do that. If anybody has questions, I'll go ahead and enable it. I'll moderate it, and if we have too many questions, then we can just unmute everybody. 1 second while I go ahead and switch it over so people can hear or can participate. Great. If anybody has questions at any time, just feel free to raise your hand, and I will let Frank know.
Okay, so what is going on here? So radio astronomy is the study of things out there in the universe that give off radio waves, right? So it's a way of supplementing, or even in some cases supplanting, we'll say, optical astronomy. We'll see in a couple minutes. I have a picture coming up that I think illustrates this really well. But there's stuff out there that we just can't see with light buckets, with the naked eye, with the best optical observatories in the world. You're just not going to be able to see through a cloud of gas, right? And again, I'll illustrate that in a second. Optical astronomy, I have a note here, it's been around as long as people have been looking up. There's tons of neat stuff to see.
I think we might have lost audio again.
How about now?
You're back. Yep.
Okay.
Go.
I want to make the point that radio astronomy is much newer. This has only been around since the end of World War II, say. And I have a list of books at the end, some things that I've read that I think are pertinent. But I think the advent of radio technology, the work that was done at Bell Labs in the last century, these things, I'll see the advent of the transistor, right, was huge, but the real impetus was radar technology in World War II that really started to, that's when this stuff really started to take off. It's very technology driven. So what do I mean by that? Optical, you sort of, they had this centuries ago. You just sort of made lenses, and sure, you can get precise, and lenses need to be shaped well and made well. But RA is definitely like.
It sounds like we might have lost your audio again.
Okay.
Sorry about that. Now you're back. You're good to go.
All right. Sorry, guys. You may be familiar with the EM spectrum. I don't know. I like this image. I would say the big takeaway here is if you look under wavelength, we're interested in, I think for some of this, we're interested in RF, HF, right? So maybe the middle. So the middle frequency. So depending on how you define a hacker, I think there are a lot of overlaps. The way folks in the radio astronomy world
I think we lost audio one more time, and I think I know what's happening. I apologize, but there is an interesting quirk that's actually for privacy. It will disable mics if you don't move within a certain amount of time. So if you wouldn't mind going and clicking on menu, and then under your audio, you can turn off mute when idle. I think that's probably what's going on here.
Okay.
And that should keep you on for the rest of the time.
Settings, audio, turn off mute when idle. Okay.
Yep, it's actually, they have that as a privacy feature so that if you forget to turn off alt space, people can't hear you talking in your room. But I think that's probably what's tripping us up. You're good to go.
Okay.
Thanks.
Let me try again. So I think there's that that maker spirit, right? These are the people at these conferences are a lot like the people at security conferences in some regard. They want to learn everything they can about a thing, right? It's almost it's that seeking out of knowledge. And I think, if you ask me, hacking is about coming up with solutions to problems, maybe in ways that the designer didn't intend, using things perhaps the way they weren't meant to be used. So this is kind of a fun point here. Novel and clever solutions to problems you didn't know you had, right? So it's doing what you need to do to get a result, and not letting technology hold you back. So they have their own tribe, as do we. They have heavy involvement in ham radio, maybe a little heavier than our community, but interest in antennas, wave propagation, chemistry, physics. So by that I mean designing antennas, designing receivers, SDR, right, comes into play. These are kind of their world. I'll say these are folks who run the planetariums, the observatories, people whose day job may be in astronomy, whose education and background may be in astronomy, radio astronomy, physics. But they do this stuff as a hobby. So, why is radio astronomy important? I don't know. I'll go through this and then I'll say a thing that I think you may or may not agree. But I think it's more than just a quest to see what's out there. I think there are questions that we don't even know to ask yet. It's a big universe. I think there's stuff out there that's, you know, these big questions that folks grapple with. Yeah, where did we come from? What's going to happen to us as a species? I don't know. Maybe some of this stuff gets into sort of religious territory, but these are some of the biggest questions we grapple with. What happens when we die? That sort of thing. Where's the edge of the universe? You know, what was before the Big Bang? That sort of thing. I think I spoke a little bit to this, that RA complements optical astronomy, being able to see things that are out there that aren't lit up, things that are dark, right? So if, and I'm not referring to dark matter, but I'm referring to matter that is dark, that has no light shining on it, right? Being able to see through clouds. So to know what's out there, to get a sense of the shape, size, distribution of matter in the universe, big reason that this is important. Yeah, this last point I think is a good one. So when we do science, when we do exploration, there are spin-off technologies that I think can make life better. So that's what I mean by that last point. Yeah, this will bake your noodle. The magnitude of time and space, right? These ideas are, I'm not even sure the adjective to use, but I'll say it like this. There's stuff out there that's just tough to think about, and if you're really interested and you click the source link at the bottom, I think that you can spend weeks thinking about this stuff, right? The size and shape of the universe, the density, the nature of time, yeah, just that. And if that's your thing, this for sure is, you're in the right place. I myself am a little more technology driven. I'm interested a little more in the data that we can collect. So Jansky was one of the first people to get into RA. He was an amateur. He was a person who was not paid. First person to record radio signals from beyond Earth, right? So I think he worked for Bell Labs. Like, the wiki page can tell you a lot better than I can, but I think while he was working for Bell Labs, the HISS that he found turned out to be the black hole at the center of the Sagittarius galaxy. And yeah, I like that he was an amateur, and I like his memorial, which we'll see a picture of in a second. Oh, his monument, there it is. So this is actually located in New Jersey. You can go check it out. I'll show a better picture of what this is in a second. This is the antenna parts of what he built in his backyard. But after him came Reber. Reber also built an antenna in his backyard, but I think his was a little more robust, right? So I think the story goes that even though he had his EE, his degree in electrical engineering, he was unable to find a job. Yeah, there's a note there. Couldn't get a job with Chansky at Bell Labs because of the Great Depression, and wound up in Wheaton, Illinois, building a radio telescope. Fascinating people, both of these men. But interesting, like this was less than 100 years ago, you know, that they started on this technology, and we'll see in a second that they've done so much with it. It's just amazing. So, how am I going to explain this? This is one of the underpinnings of radio astronomy. The ability to see based on the emissions, right? So hydrogen is spinning and it gives off radio waves at a certain wavelength, which is how we know it's hydrogen. So other elements also spin but give off emissions at different wavelengths. So you can look at these and say, okay, now I know I'm looking at hydrogen. I know I'm looking at, you know, whatever that element might be. So yeah, more prevalent, penetrate faster and farther than visible light. That's huge because we can use that property to see farther.
We may have lost audio one more time. Just double check that mic.
But I want to show, how about now?
Yep.
I want to I want to make a distinction here between the picture on the left and the picture on the right. So you can see the caption stellar light, which just means starlight, right? So the light coming from those stars, we get a picture that's not as detailed as the picture on the right. Typically what you'll see in RA is what we call false color images. So this would be the distribution of hydrogen, and you can see you get a very good picture of a whole galaxy there, right? You can tell now that it's a really well-defined spiral galaxy. It may have collided with something else, like whatever's going on in that picture. I think I have an actual clickable link in the original presentation to the group that did this research, but it's just fascinating stuff, and illustrates that principle of that radio does a good job of complementing and sometimes not just augmenting, but more than augmenting optical. So, interesting. Interferometry. I'm going to tell you about this, and I'm telling you this stuff for a reason, because I'm going to show you some fun pictures of different facilities and stuff, but let me try to explain this one. So, what we're going to do with interferometry is point at a thing. So in the picture on the left, I'm looking at the red dot in the top right of the picture. It's got the little green stuff around it. And the wavefront is coming down across the dish for 2 receivers. Okay. So what we can do is not link, you don't have to link, but you do have to collect the data with a very accurate timestamp at both of these dishes, and then using some simple geometry, you can get a better picture, I'll say. So I'll say it like this. Let me say one more thing. The C on the left is like the speed of light. So you know the speed of light, you know B, the baseline. If you look at the picture on the right, you can use simple, fairly simple geometry, right? So you know the angle theta. You take the cosine and sine of the angle theta, which is from the baseline to, well, the angle theta there. You do that math, and you can correlate the data between these two scopes. Okay, let me say this about it. If you have a bunch of radio telescopes and you link them electronically and you move them very close together, what you can do is take a very wide picture of the sky. If you take this same group of radio telescopes and you spread them apart, you can focus on a very narrow point in the sky. So that's the premise behind the VLA, the Very Large Array in Socorro, New Mexico, right? These dishes are on train tracks, and you can move them closer together, farther apart, link 2, 3, 10, all of them to do observations. So interferometry technique is how we get better pictures, better resolution. And there's, I don't know if it's in this one, but there's very long baseline interferometry where the scopes are really, really far apart. Now they're talking about building a radio telescope on the dark side of the moon. Imagine the baseline, right? Look at B, baseline in green on the left, between Earth and the moon. Much longer baseline. So I just showed this to say that for people who like computers, I think this is an interesting way to get involved. So the amount of data when you do interferometry, for example, is large. Being able to process that data in a time that researchers need to be able to look at it, right, to get their papers written, to get, I don't know, for the end of the semester or whatever thing, right? So you need to be able to post-process data in a timely manner. That's key. The correlation of this the interferometry data can be challenging. Why? Because of time. So you have to have very accurate, precise sync of your clocks, right? So like, I don't know what that would be, like stratum 1 NTP, or is there even a stratum 0? I don't know, but very precise time. This is a great use case for computational clusters, right? So if you're into clustering, this gives you an excuse to build something, and this gives you some data to crunch for sure. You also have issues related around very large data sets. How do you move those from the observatory in South America to the university in the United States, right? When it's just terabytes of data, and do it in a timely manner, and so on. So especially from a remote area, you see this kind of challenge come up over and over, right? Like scientists are in Antarctica, scientists are at the North Pole, scientists are in the mountains in Chile, they're in observatories, and you're trying to get this data back to the universities and stuff, so it can be tough. But I think all of this, if you're into like technology stuff, and I'll show you a way that you could really like real life get involved, go do this in a few minutes, but this is huge. This is kind of where the fun stuff starts. So I want to shift gears a little bit and talk about some time that I actually got to spend doing this stuff at a national, NRAO is like the National Radio Astronomy Observatory. It's an organization like any other federal agency, I guess, but it's mostly educational. Excuse me. So this is a trip that I took to Green Bank, West Virginia, and I'll tell you in a second why this is special. But if you look in the background there, I want to say this was the scope that this is a replica of the scope that Reber made. So we're going to see in a second how this would be an example of a scope that's used for direct observation. So there's this, and as you drive in, you can kind of see my car mirror as I drove in there. So, what does one do at a radio astronomy conference? This conference was actually put on by a club called SARA, so it's Society of Amateur Radio Astronomers, and these are folks who, again, they're it's not formal, anyone can join, right? So they get together, do talks, that sort of thing. So show some more of that in a second. This is, I think, the main building as you drive in, but this is a government facility, so. This is one of the main buildings, and kind of the cool thing, like if you're one of the in people at the club, you get to stay in these dorms. Those on the top are like dorm rooms with bunk beds and that sort of thing. And then on the right there's a cafeteria. The thing that stood out to me about the cafeteria was they had, scratch paper pencils everywhere, because folks would just, like, these are some smart folks that work there, right? So their brains just pop in, they have to write stuff down, there's math everywhere, like, they're into it. And I think with good reason. This is some fun, interesting stuff. So this gives you a sense of what that building looks like. Very, not stark, but governmental. So here's a couple club members, and this is the Frank Drake Lounge. And if you know, if you've ever heard of the Drake equation, this is the equation that is meant to, well, we'll say it's meant to calculate the probability that the possibility of how much intelligent life is out there, right? So this isn't a great picture of it, but you can see that plaque above the fireplace. The brown plaque there is actually the Drake equation, because this room is where Frank Drake was when he came up with this. So it's a pretty cool place to hang out. You can see there's a small library on the left. What else do I want to say about this? So this was in the common area of the dorms. Pretty cool history in that room. So I showed this, like, the scientists, the federal employees, the people that work there, they were really cool. They were really accommodating. And I felt like it was good bang for my buck to get to go out here, see this stuff. And not only that, they were just nice. They're like, hey, here's a bunch of stuff we can't use. It's old radio equipment. I'm not going to remember what everything was, but old receivers, feed horns, antennas, whatever it is that they felt like they didn't need. They opened that up for us, and folks were able to, I think we actually raffled it off. So come pick through that stuff, kind of fun. I want to see if I can find this gentleman's name, but he's one of the, I think he was a machinist at the facility. Gary Anderson. Okay, so he's talking about the calibration of the 327 megahertz feed for the 100 meter telescope, which we'll see in a second. So a feed is like, if you imagine a parabolic dish, imagine a bowl shape. It's convex. There's what they call an aperture. So imagine if you're holding a bowl in your hand and you put your other hand on top and then drew it up in the air and pinched your fingers. I'm kind of making a strange motion that I'm having trouble explaining, but the apex of when your fingers all come together is the aperture. It's where the feed horn goes and collects all the signals that are reflected from the convex dish, from the parabola, the parabolic dish. So this young man, that was his job, right? To calibrate these things. So there's very sensitive radio equipment involved in this work. So what do I mean by that? Well, it's it's so sensitive, in fact, that it needs to be kept at certain temperatures, right? These receivers need to not just be calibrated, but sometimes cooled. You'll see in a lot of amateur rigs that they will put their stuff in an ice chest. I think even with dry ice, like folks get really into it. And this is the reason, because you want to have a clean signal, you want to take away degradation, background noise, hiss, whatever it is. You want to get the cleanest data you can. So that's Gary's job. Pretty cool. We felt really special to be able to go in here, but the big thing, so why West Virginia, right? So the big thing about this area is that it's designated a national radio quiet zone. No cell phones, no FM radio stations, no AM radio stations, no cars that don't have a diesel engine. So that's what this sign in the picture is showing. A car with a spark plug gives noise. That noise, that heat, that signal that's coming off your engine can be detected by the scope that we're about to see. Well, the one we'll see at the end, but that's the reason for the National Radio Quiet Zone, to do everything we can to minimize the potential for interference with these very hard to calibrate, expensive to maintain dishes, right? So let's see here. So these this baby blue fleet of vehicles here is how they got around. That and bicycles. I think you needed certain permission to drive the cars, but anyone could ride the bikes. So I wound up riding the bicycles when I wanted to get around. So yeah, there they are. Here we are in San Juan. This was one of the club officers who actually had permission to drive the vehicle. So let's go for a ride. And he's going to take us, I don't know if you can see sort of through the windshield on the right side there. We're going to go over to that radio telescope. So this is the 40-foot radio telescope. So this is an older scope, a smaller scope. But hey, it still works, right? Like they would train students on it. There, you can go right now to nrao.edu. Or is it, I think it's edu, not .gov, but you can go to their website and download the guide for how this works. What you need to do to get set up to do observations from this location, right? Like this is out there. You can go do this stuff. I think you need special permission to go down there. Our club got it. You probably could too. You could just join the club. I don't know, but the other cool thing I'll say about this is it wasn't just radio quiet. Like you could look up and just see the Milky Way. I had never experienced that, being mostly from the city, right? I never saw the Milky Way that way. So we spent, I would say, a good 2-3 hours just laying on our back in the grass, like, holy cow, look at that. I mean, it's fascinating stuff. But anyway, so we didn't sleep much. Like we wanted to make the most out of this time, so we actually spent a lot of time in this room because we were allowed to do stuff. So here we are going into this place where the back end electronics are kept for the 40-foot dish. So again, these are receivers, right? So you're going to take the RF that comes from the dish, you're going to turn it into IF, right? And then eventually down convert it into AF or data. You're going to put it out on a serial port, something that you can listen to. By AF, I mean audio frequency. By data, I mean points and stuff that you can plot onto a strip chart. I think there's a photo of that coming up. But essentially, that's what all these electronics do, is down converting the signal and doing our best to maintain that fidelity between what's out there and what we're capturing. Right? We want the highest degree of fidelity possible. We don't want a bunch of noise. We want to know that, hey, we got a good observation. So that's what that is. So we're goofed around a little bit, but yeah, there's actually a strip chart. It was fun. It was interesting to work on. It was cool to be that close to that much history, right? Because this stuff's been out there for decades. But I want to say a lot of this has been supplanted by technology, right? Like, why put everything out to a strip chart if you can go pick up a Raspberry Pi off Amazon and, right? Like, that's your pivot to something much more interesting and exciting to do with respect to post-processing your data. You can see a couple of scopes over there. So you could, right, like you could look at this stuff as waveforms, you could look at this stuff as traces on paper. So let me give an idea. Like if you were to tilt, I don't know that dish rotated, but if you were to tilt that at the sun, you would see a spike when it got close to picking up signal from the sun, and then as you tilted the dish away, you would see the line drop off. If that gives you a good mental picture of what you might see on a strip chart. So this is the big tamale. This is the Green Bank telescope. This is this is their bread and butter, right? This is what astronomers want to come observe on. You can get some sense of the scale. You can see in the middle bottom, there's a couple cars and trucks down there. It's huge. It was massive. Let's see. I think right down the middle, those were Those were for elevators. But taller than the Statue of Liberty. This thing was just large. Interesting thing about this picture, like all that scaffolding underneath is just support. The electronics of it is, I don't know, like when I look at this, I try to imagine it without all the framing on it. I don't know. Anyway, I want to point out that the thing at the top middle of the picture is the feed horn that I described before. So signal comes down, hits the dish. This one is fully steerable, so you can aim at things, right, to do observations. You're going to want to use the rotation of the Earth to help you aim, but this you can aim more than the 40-foot, for example. So what we're going to do is reflect all the signal from the dish, right, from all the way around the edge, all the way down to the bottom, at that feed horn, and then take that RF down that long line, that dark line on the left side, across the bottom, and then down where that sort of elevator part is. You can see the black, I think, going straight down is kind of like what you'd see on a cell tower, right? It's, I think it's either copper or waveguides. It's probably copper to carry RF. It's not high enough for waveguide, I don't think. But again, not a cosmologist, not an astronomer, don't quote me on that. So, but very cool. The nice thing about this, as a club member, they took us right up to the scopes. Like we got to, it was like all access behind the scenes. We got on the government bus. They rode us down there, gave us hard hats. Like everyone else had to be behind the fence a mile away. I don't know. It was fun. It was really cool. So I'm running kind of short on time. I want to show some more stuff, so I'm going to speed up a little. Oh, good. So we're at this part. So this last group of slides, and again, there's clickable ones out there if you're so inclined, it's meant to be stuff that you can do. These are ways that you can get involved, or at least get started if you're really interested. So this first line says, JPL made a great primer for Radio Astronomy in '98. There's a place in California. It's called Goldstone Apple Valley. So if you're familiar with the Deep Space Network, they do things like track Voyager, Voyager 2. They talk to spacecraft that are far away on Mars. They help. There's a place called Parkes in Australia. So when something they want to see or talk to is on our side of the Earth, like they'll cooperate with Australia and they'll pick it up when it's on their side of the Earth. Anyway, they also use the Goldstone Apple Valley Radio Telescope, hopefully I said that right, for observations. They wrote a book on it. It's really good. It's really good. And it explains interferometry, the 21 centimeter hydrogen line, like all these just fascinating like precepts. Is that the right word? I don't know, but all these really interesting things about radio astronomy. And it's so accessible because it was written for teachers. It was written for educators to bring school buses of kids out to this radio telescope so they could teach their classes. Like, it's a really good PDF. It's a little over 20 years old, but definitely check that one out. So NRAO, again, had a Getting Started site. The SARA conference, the one I went to, is August 2 through 5. This year they have a call for papers. I think their conference, like a lot of things this year, is going to be virtual. I wouldn't let that stop you from checking it out. They have also met in the past at Stanford in California has a scope. They did a West version of their conference there. I think they've been out to the VLA. If you haven't been to the VLA, that's fascinating stuff. That's in Socorro, New Mexico. That is a very large interferometer. Imaging. So I made this slide to make the distinction that there are two kind of ways to do radio astronomy. Imaging is a dish. Imaging is you go hijack an old direct TV receiver and you make your own back-end electronics and you do some observations, right, by pointing it at things like Jupiter, perhaps. So this is a 21 centimeter observation of what Jupiter looks like at a lower than visible frequency. So if you look at Jupiter, right, we've all seen that picture on the bottom, but if you look at Jupiter through your radio telescope, it looks quite different. And UHF, VHF, EHF, so kind of in the middle to the left of that EM spectrum diagram I showed. And imaging uses broadband receivers, and that link down there shows there's actually like an open source radio telescope project. There's, let's see if I have some here. What did I put? Oh, here we go, good. So there's tons of this stuff out there. 20 years ago, this stuff just wasn't as prevalent, right? I think the prevalence of the maker communities, low cost, low power electronics like Raspberry Pi stuff, like this stuff has really taken off, and it's accessible and it's not as difficult, and there's trailblazers out there who have done it before, but there's also a ton of greenfield interesting stuff that you can go work on and make a valid contribution. Like, remember this guy on the right over here, these weren't pros. Like, they just went out, listened to stuff, discovered things, wrote stuff down, helped out with this new field of science. And again, I think there's a ton of greenfield with respect to the interferometry, the large data sets, and all that stuff. And I promise I'm going to show a fun way to get involved with that. But there you go. There's some links right there. So here we go. This place is Pisgah Astronomical Research Institute. You can go there. You can volunteer. You can visit. You can do observations. You can bring your school bus of kids out there. You can do your PhD thesis there. You can get a sponsor to bring, like, all kinds of cool stuff that you can go get involved. And when I talked to these guys, the kind of problems that they mentioned to me were, hey, we have all this data. What the heck do we do with it? How do we secure this stuff? How do we, like, they have their own software suites, right, that need contributors. If you know Python, right, there's a ton of ways to get involved, and I think it's very noble. Good way to spend your time. So, I have a little note in the middle there. Former NASA, air quotes, research facility. So I think what they used to do was aim these at telecom satellites, maybe 1950s, 60s, 70s-ish. I don't know. Why would they do that? Why would the NSA do that? Who knows? Anyway, so I made the distinction of imaging. This is indirect observation. So there's ways to collect signals without a dish. That's what I want to say. So different set of frequencies, narrowband versus the broadband, wideband receivers. For example, Stanford did this ionospheric disturbance. I don't know, we'll call it a box. So sunspots. Hey, some solar event, right? Hey, we got this big spike at this frequency. We know it was a sunspot. We know that that's important because in 8 hours or however long the time is, we're going to have a thing that impacts the telecommunications satellites, all your direct TV receivers, whatever it is, right? Like this stuff is important for those reasons. Pretty interesting. Radio Jove. It says decametric telescope. Basically, it looks like a bunch of clotheslines, but deca, right, I think means 10, I think. Again, I am not a astronomical lawyer, but I have seen this. It's pretty cool because what people do is set these up, build the receiver, and then share the data. So you can join a network of other people that are actually doing this stuff. It's really cool. This one is paid for with your tax dollars, so definitely avail yourself. Radio Jove is out of, I think, JPL in Pasadena. I put a list here of books. So Astronomer by Chance is fascinating. Bernard Lovell is a gentleman who, at the end of World War II, I want to say during the war he was doing stuff with radar. I haven't read this in a couple of years, but he then after got into radio astronomy, right? So just like the title says, astronomer by accident, by chance. I mentioned parks, pretty cool. Our friends down in Australia. Anyway, you can look at these. I think that's it. Oh man, I want to say, definitely check out the Launch America website if you're into anything space. 27th, they're going to launch one of these Falcon Heavies with 2 astronauts on it. Like the United States return to human orbital space flight. Like that is amazing. Definitely check this out if you like space stuff. But I think that's it. Thanks for everyone who reviewed this. Thanks for checking my stuff out. And if you want to get the links, I'll put them on my Twitter. And thanks for having me.
Awesome. Thank you very much, everybody. Let's see a round of applause for Frank. So I have enabled the hand raises. I think we had it on most of the time, but it disappeared for part of the talk. If anybody has any questions, feel free to push that raise hand button and we can give Frank questions. Otherwise, we'll open up the room for general chat in just a few minutes. One more shameless plug for Alt VR, just because they've been so supportive of this conference and so awesome. I know that they have regular launch parties for SpaceX launches. So if you want to watch a SpaceX launch with several other people that are interested in the same thing live, AltSpace VR is a really cool place to do it. And I've heard that there's actually some SpaceX people that occasionally will drop in and watch in VR during the launch. So if you love space as much as Frank and I, this is a great place to hang out. So wonderful. Well, I will unmute the room. If anybody has any questions for Frank, feel free to come up to him afterwards. Just a reminder, we will have an after party. We've got one more round of tracks after this. We have Jason Street speaking on just hacker things. It's going to be a Q&A and just him sharing some thoughts with everybody. And that will be in this track. In the Palms, we have Eric Escobar and Matt Orm talking about your corporate networks are showing. They're going to be talking about a really cool wireless platform they put together for actual remote wireless testing. So those are coming up. After that, we have the InfoSec OASIS after party. It is a private party, but we have published the RSVP link via Twitter and Discord. So make sure to check that out. It's going to be a lot of fun. We have an acoustic set at 7 Central. And then from 8 to 10, we have an awesome set by Trash Panda, who's a AltSpace VR regular and puts on an amazing show. So with that, thank you very much, Frank. We're going to go ahead and get set up for the next round of talks. I will go ahead and unmute the room.